let's say we have a car moving around a circular track and we're watching it from above. The car is not moving clockwise, instead it's moving counterclockwise, or as we say in IB terminology, anti-clockwise. That's the direction the car is moving in. So the car starts at some initial position here, and after some time t, the car winds up at this final position. Now, I'm going to make an analogy to a person who is walking forward. The displacement that the person undergoes is delta x, or in IB, we'll sometimes call that s. And what else do we know? Over here, displacement is occurring, but it's not displacement along a single axis. It's displacement along an angle. So let me mark a radius to the car's first initial position and the radius to the car's final position. As the car swings around the circle, it travels some angular displacement, theta. Theta is the angular displacement. So where regular displacement is how far forward a person travels, angular displacement is how much of an angle the car travels. Now, it's possible for a person to move this distance s in a really short amount of time. If that's the case, then we say the person's velocity v is equal to the distance over the time. And when the velocity v is high, that means the person is moving really fast. Right? In the same way, we can define angular velocity, omega. The angular velocity measures how quickly the displacement occurs. So, similarly to this equation, angular velocity is the displacement over the time. Now, angular velocity is a vector, but we'll learn in class how to get the direction of this vector. In the problems we'll be solving, we'll imagine that the car, or whatever object moves, has a constant speed, v. And let me write v over here as well. I figured out where v should point by considering the right angle from the radius. In this context, where we have an object moving around a circle, we want to distinguish this speed from the angular velocity, or the angular speed. So we call v, in these contexts, we call it the linear speed, or we could call it the linear velocity. It is also sometimes called the tangential speed, but the term we'll see more often is linear speed. And the reason we call it linear speed is to distinguish it from the angular velocity, or the angular speed. There's an equation that relates the linear speed with the angular speed. Here's the equation. Linear speed is equal to the radius of the circular path times omega, the angular speed. Now, something worth noting, when I write v with the arrow, that means it has direction like arrows, and I'm talking about velocity. V without the arrow is just the speed. Omega with the arrow is the angular velocity, and omega without the arrow is the angular speed. The velocities have direction, but the speeds do not have direction. They're just scalars. Let's take this equation and examine it a little closer. Let's say we have two flies sitting on a record, and the record is spinning around clockwise. Right here is the center of the record. The question is, which fly, A or B, has a larger linear speed? Now notice, fly A is going to move around a circle with a larger radius, and fly B will move around a circle with a smaller radius. They have the same omega. How do we know that's true? How do we know they have the same omega? Well, because they're both circling at the same rate. and the time it takes A to return back to where it started, B will also get back to where it started. So both of the flies travel the same theta, the same angle, per second. Alright then, if fly A has a bigger radius, then fly A will have a larger linear speed. So we could draw that linear speed and say, okay, fly A's linear speed is something like this, and fly B's linear speed is smaller, so a smaller arrow. How did I know to draw the velocity vectors off at this angle? I simply imagined a line going from the center to the fly, and then I drew the velocity vector perpendicular to that radius line.